Hey guys, a car is driving along a circular track at a constant speed of 60 kilometers per hour. Find the magnitude of the acceleration of the car, A. Okay, so let me break down what we're doing here. We've got a car which is traveling around a circular path, hence it abides by circular motion formulas, and at this instant it's got a speed of 60 kilometers per hour. The radius of this track is constant and it's 100 meters. Find the magnitude of acceleration. So before I go into solving this problem for you, I figured it would be worthwhile to break down the intuition behind circular motion and to re-describe the formulas for you. So the first thing you need to know is that the velocity of an object going around a circular path will always be tangential to the path. So let me draw that for you. You've got your velocity vector v of your object going around in a circular path, and that vector, v, just here, is going to be tangential to your path. Okay? That's your velocity vector sorted. Now let's talk about your acceleration vector. Well, the acceleration is slightly different. It will have a component which will be tangential to the path, and we call that at. And it will have a component which will be normal to the path, and we will call that an, right? But the actual acceleration vector is the combined vector sum of both of these. So your combined vector will actually look like this. This will be your acceleration vector. Notice that your acceleration vector is really just the hypotenuse of a triangle where an and at are its sides, right? So let me reestablish this. Your acceleration vector is just a regular vector which is defined by at in the tangential direction and an in the normal direction. Now, what is an and at? Well, fortunately, we've got mathematical equations to use. We know that our acceleration vector can be written as en plus at where en and et are something mathematicians called unit vectors. You don't need to know that, but it's just know that these are unit vectors and they just denote direction. An is the magnitude of our acceleration in the normal direction. At is our magnitude of acceleration in our tangential direction. Now, if we expand this formula out, an can be written as v squared divided by r, right? And we've got en here, sorry. And at can be written as v dot, and we times that by et just here. Okay, so notice an is v squared on r, and at is v dot. Now let me talk about what these terms mean. V is your speed. So it's not your velocity, it's your speed. V is your speed, and that's your magnitude of your velocity. In this case, it's just the scalar. It's 60 kilometers per hour. So it's 60 kilometers per hour. It's your speed at the instant, which is 60 kilometers per hour. And if you were to convert that into SI units, you'd go 60 times by 1,000 meters divided by 60 squared seconds. And I think if you plug that into your calculator, you'd get 16.67 meters per second. Okay, so that is your speed of your car at that instant, at this instant shown just here. Okay, now R is the radius of your circular path at that instant. Well, fortunately, this entire path is circular, so you can easily tell that the radius of this path is actually just 100 meters. It's the same as this radius just here. It's 100 meters, okay? Now, we're missing this term. What's v dot? What is v dot? Well, v dot, that's using Newtonian calculus, it's dv dt, right? And that's just your derivative of your speed. Now, this is where this description in the question becomes actually quite important. It was pretty subtle for me to sneak it in there, but it's actually really important. Because this car is actually traveling around at a constant speed, so it's not like driving faster and faster or getting slower and slower, that means its velocity is constant, which means that the time derivative of a constant is 0. Okay? Okay, so that means v dot is 0 because the derivative of a constant is always 0. All we need to do now is plug it back into here. So what is this? Well, v squared on r is the same thing as, let me write it down, 16.67 squared divided by 100. Notice that I'm only using SI units. That's a very good habit to get into. Times En plus V dot, which is 0, as we just discussed, times ET. And if you were to plug that into your calculator, you'd get, let's see, 16.67 squared divided by 100. That's 2.78 meters per second squared. And don't forget we times it by our unit vector again, plus 0 ET. Well, because this is a 0 here, we can actually ignore ET, or you could continue writing as 0 if you like, but I'm just going to ignore it because there's no component. So hopefully this isn't just a mathematical construct for you. We can describe this visually. So let me quickly redraw our graph just here. We've shown that our acceleration of our car has no component in the tangential direction. This doesn't exist. There's no component in the tangential direction. It's purely in the normal direction, and it's got a magnitude of 2.78 meters per second squared. So our acceleration is purely in the normal, and it's 2.78 meters per second squared. Now, in case you're not completely convinced that the magnitude of this must be 2.78 meters per second squared, let me prove it to you. We know that the magnitude of our vector is given as the square root of an squared plus at squared, right? That's just using Pythagoras. And in this case, this is going to be 2.78 squared plus 0 squared, which you don't need a calculator for that. That's 2.78 meters per second squared. This is the magnitude of your acceleration vector just here, okay? All right, I hope that explains it. I know circular motion can be pretty tricky when you start off because you've got this really crazy expression just here, but I'm sure if you stick with it, you'll get it just fine.